Hi, we are Team Shunya, the Mass Rover Students Club of IIITDM Kancheepuram. We are an interdisciplinary team of 25 plus engineers from various backgrounds mechanical, electronics, software, and science, all united for one goal to design and build autonomous rovers and drones capable of navigating through some of the most challenging environments on Earth and eventually beyond.
Our team is headed by a team lead, assisted by a technical lead who oversees all technical operations, and a team manager who takes care of planning, logistics, and everything that keeps the team running smoothly behind the scenes. Each of our 6 sub-teams mechanical, electronic, software, science, drone, and management is headed by a dedicated sub-team lead who drives their domain forward and ensures every piece of the rover comes together as one cohesive mission.
Why ERC? At Team Mars, we are continuously driven by a relentless passion for autonomous systems and space technology. Over the years, we have continuously pushed our boundaries, achieving 4th place globally in the ERC Remote Edition 2025 and earning top innovation awards for our autonomous navigation stacks. We are running in ERC 2026 because there is no better proving ground for testing UGVs in space analog environments. It is the ultimate stage to validate our latest advancements in real-time SLAM, sensor fusion, and robotic manipulation against the highest international standards. For us, ERC is more than a competition. It is a vital stepping stone in engineering the future of extraterrestrial exploration right here at IIITDM.
This time we have developed a custom-made silicon grouser with a split chevron thread pattern mounted on a hybrid rim made up of aluminum 6061 plates and a reinforced PLA core. These provide the excellent traction, shock absorption on a loose and wet terrain, enabling the rover to overcome the obstacle up to 25 cm. The wheels are driven by the high torque 352 kgcm DC planetary gear motors through a bearing supported wheel mount for reliable performance. The suspension integrates with a 4-wheel independent steering system capable of full 360-degree rotation. This time we upgraded our steering mechanism from a normal spur gear system to a 5:1 warm gear setup for more precise and controlled steering. The steering is powered by 150 kgcm DC planetary gear motion and coupled to a wheel mount through a hexagonal stud, enabling the advanced mobility such as crab walk and spot turn Ackerman. We upgraded from a rectangular bar suspension to a 4-wheel V-shaped suspension with a cylindrical bar connected through a differential mechanism, improving balance, durability and ground contact while keeping the center of gravity low. Currently we are using 38 mm outer diameter aluminum pipes with plans to shift to a carbon fiber pipes for reduced weight and higher strength. The rover uses a 600 x 600 x 300 mm modular aluminum extrusion chassis reinforced with aluminum plates and a carbon fiber base plate for mounting electronics and software system. The chassis also integrated with the science cache and the manipulator arm on the opposite side for the balanced weight distribution, while the suspension is connected through the ball bearings and washers for the smooth and reliable operation.
At the core of our electronics, we use 4 ESP32 modules for steer, drive, manipulator and science, which uses PID loop mechanism for precise rover movement.
We have upgraded our custom PCB from last year, which ensures better debugging and precise power distribution. We use 24-volt battery supply, which is stepped down to 18, 12 and 5 volt respectively to control the motors and peripheral electronics. We have also upgraded our manipulator's communication protocol from UART to CAN bus, ensuring better noise immunity and proper control over the motors. A relay-based kill switch is being used to control the power to the entire rover without affecting the communication system. A remote-based kill switch is being implemented which can be controlled from the base station.
For our communication with the rover from the ground station, we use Ubiquiti Rocket M5 antenna, which operates at 5 GHz frequency, has more than a kilometer of outdoor range, and has low latency link with the rover. For safety measures, we have hardware-based limit switches that restricts the rover's movement and gets it into a safety position, such that it does not move unpredictably and uncontrollably during primary communication loss or in case of a component failure.
Our autonomy stack is developed and validated in simulation. A high-fidelity URDF replicates our rover's exact physical configuration, chassis dimensions, wheel geometry and sensor placements, ensuring the areas validated in ignition gazebo translate directly to hardware. Sensor data from a virtual depth camera, IMU, GPS and wheel encoders feeds directly into NAV2, which handles autonomous navigation via A-Star Global Path Planning and built-in recovery behaviors for obstacle handling. A custom low-level controller then processes the resulting velocity commands for precise Ackermann drives, spot turn and holonomic motions.
For environmental perception, our Z2i stereo camera captures RGB and depth data in real time. These images undergo filtering to improve depth quality, while echo detection and object detection identifies target in the sea. By combining this detection result with depth information, we compute accurate 3D coordinates required for navigation and manipulation.
For unmapped terrains, we run RTAP Maps LAMP, building real-time 2D occupancy grids and 3D maps, driven by dense depth images and visual odometry from the Z2i stereo RAM. Wheel odometry, IMU and GPS are fused via an extended Kalman filter for robust global localization and state estimation. The global cost map uses a voxel layer inflated for safe scaling, while the local cost map leverages the Z2i point clouds through a spatio-temporal voxel layer followed by inflation, giving nav2 accurate dynamic obstacle awareness for reliable navigation.
Our aerial platform is built on the S500 quadcopter frame. Its open center design provides optimal avionic access and clean cable routing across all four arms. Propulsion is driven by 4 dedicated brushless DC motor rated at 1000 kV each, paired with an individual electronic speed controller. This isolated configuration ensures high per motor control resolution and prevents fault cascading. A 4S 12,000 mAh LiPo battery yields approximately 20 minutes of operational flight time.
We have designed an 6 degree of freedom serial manipulator with primary joint using a custom developed cycloidal gearbox, providing high torque and minimal backlash. It has an 1.5 meter reach and 5 kg payload capacity. Removing the plates, now we are using 30 x 30 square bars with link length of 500 mm and 600 mm for link 1 and link 2 respectively. A bevel gear differential mechanism coupled with two 150 kg DC Planetary gear motors provides roll and pitch motion to robotic gripper. We have changed to a dual 4-bar linkage gripper system. It is moved by motors using a lead screw mechanism. The two jaws are set 18 cm apart so the gripper can clear the obstacle and pick up rocks up to 15 cm in diameter. This dual gripper setup is made for maintenance tasks and surface sampling. It uses a special finger attachment to scoop subsurface samples weighing more than 100 grams. By putting two grippers at the widths, we made the manipulator more flexible and gave it more reach. This helps it do many hard jobs in the field with high precision.
Building on the perception data, the manipulator pipeline converts the target's 3D coordinates into the robot's base strength using TF2. To handle complex tasks, we use the movie task constructor, breaking the operation down into simpler steps like approach, execution, and retreat. For final high-precision alignment, a wrist-mounted webcam provides close-range feedback. Movie utilizes the RRT algorithm to generate a smooth, collision-free trajectory, while the track inverse kinematic solver handles fast, reliable inverse kinematics. On the hardware level, this trajectory is executed by a dedicated PID control loop on each joint, minimizing position error using real-time encoder feedback. Finally, the arm returns to its home position using encoders and limit switches.
For the Astrobio task, we have made another end effector design. For liquid environments, we have integrated a pH testing probe directly into the end effector, enabling real-time chemical analysis during the mission. Additionally, the end effector features a syringe-based suction system to draw and safely store water samples for subsequent examinations. Transitioning to our surface sample system, we feature a dedicated science cache. The science cache houses separate storage containers for regolith, rock, and deep core samples, each integrated with a load cell for precise individual weight measurement. For immediate surface operations, our custom engineered gripper seamlessly transitions between loose soil scooping and irregular rock collection. The jaw geometry and actuation were precisely modeled to guarantee secure sample retrieval under varying payload conditions. Deep sample extraction, we utilize an Archimedean drill mechanism. While our previous design could successfully extract a soil from depth of 10 cm, the design has been optimized and upgraded to extract soil from depths more than 30 cm. For this year's science exploration mission, our primary target is Hellas Planitia, one of the most scientific, compelling impact basins on Mars. To analyze this terrain and map our traversal routes, we are utilizing JMars as our primary visualization tool. As you can see here, the terrain presents unique challenges. To safely navigate and characterize this environment, our rover will continuously monitor critical atmospheric data such as pressure, humidity, temperature, and altitude via our onboard sensor suite. To analyze the soil type, we are using a Munsell chart machine learning model such that we can analyze the color of soil and also estimate its properties.